In the last video, part 1 of this series, we walked through the building blocks of this temperature and humidity sensor board and covered a good portion of the schematic. Make sure to check it out here. In this video, we will continue our journey through the rest of the schematic, and before that, I want to give a quick shout out to today's sponsor, PCBWay. If you're looking to turn your electronics projects into reality, PCBWay is the place to be. They offer top-notch manufacturing services, fast turnaround times, and excellent customer support. So whether you're a hobbyist or a professional, PCBWay has got you covered. Check them out today and turn your ideas into reality. Right before that though, let's just go down to the schematic right over here where I get the same power, which is this V-bus, and I feed it directly to this LDO. This one is a fixed 3.3 LDO, and it's a high PSRR, which is a power supply rejection ratio. For this particular design, I picked the 3.3 because 3.3 is the rail that works for both the microcontroller STM32 as well as the humidity and temperature sensor that we're going to talk about in just a second. So we have this one 3.3 rail that's going to be for housekeeping, and it basically powers everything on the board. And again, even though we have this LC filter on the input of this USB connector, it's always a great idea to have another LDO to filter out noises at higher amplitude, and it gives us a better dynamic range for all the noises that may potentially exist on the V-bus net. So here we get the 3.3 typical design where you have decoupling caps on the input and output. And again, for any sort of an LDO with relatively good PSRR, you can increase the dB amount for the PSRR bar by increasing the output capacitor. So 2.3 microfarads was recommended by the datasheet. I just left it there. Again, I don't need that high of a PSRR. Currently, I believe it was about 50 to 60 dB for the frequency range that we expect to see on the V-bus. But since I also have an LC filter that does a lot of the filtering, we also add the LDO. It's going to be just fine. So we have a clean 3.3 volt output, and here I just have LED indicators that indicate if the V-bus is connected and it's drawing power, and if the 3.3 volt is on and running. And it's just a simple Ohm's law. You have a 4 voltage of this LED, 4 voltage of this LED, and the anode connected to the 3.3 and the V-bus, and you just kind of have to find the resistance that limit the current enough so it doesn't burn out. So it's very simple, right? You basically just do V-bus, in this case 5 volts, USB is a 5 volt device, minus the 3.9 volt forward voltage of this LED, and then you divide it by the amount of current that you want to feed through this LED. Obviously, you don't want to draw too much power because you don't want the board to be drawing too excessive amount of power, because then it's going to get hot and the USB only has a certain amount of power that it can provide. So you don't want to exceed the amount. So in this case, I just picked about 5 milliamp for both of them, just so that we have enough current that lights up the LED so we could actually see it, but also it's not too much that it's gonna exceed the USB rating or the thermal requirement of the board as well. Now the next step is actually just the brain of the board. In this case, I picked this STM32 part. As you guys know, STM32 is a pretty versatile chip. You could use it for industrial, automotive, hobbyist. So for this chip, I'm not using so many of these pins because it's a very simple board that we're trying to use mainly for sensing temperature and humidity of the environment. So we don't need that many peripherals. Here, as I discussed, we have the DN and DP, which is the data lines for this USB. This particular chip already has a data USB transceiver inside, which basically just converts it from USB protocol to UART that is processable inside the chip, and that's why I just feed it directly to these two pins. You cannot connect this to any other IOs unless you have a USB transceiver outside, but in order to make things easier, I just have it directly inside. For any USB differential pair, you do need to have some sort of a matching network where it ensures that there won't be any reflection on the bus, because this is a relatively high speed trace. But this chip, as I said, since it's particularly designed for USB applications, it does not need any matching network because it is internally compensated. So you do not need any resistors or any RC network, for example, on these two lines. And on top of that, as I said, since this chip is particularly designed for USB applications, it does provide direct programming and debugging over USB. So the same USB that you connect to power the board, you could use to flash this microcontroller. But for the sake of redundancy and adding a little bit more flexibility in the way of debugging and playing around with some of the peripherals, I also added the SWD interface for programming as well as debugging. So we have SWD IO and SWD PCBW clock, which you basically use to program the chip. And on the right side, I'm using just one of the IOs for indication that the chip is alive. So this heartbeat LED indicates when the chip is getting programmed. You could adjust the status of this IO however you want, but normally when the chip is getting programmed, we pull this pin low in periods of, let's say, half a second or something, just to ensure that the chip is alive and you're able to communicate with it and flash it. And when you pull this pin low, toggle this pin, you'll see that the current will get drawn from this 3.3 volt rail and it'll turn on this LED. Right after that, we have the I2C protocol. The I2C is the main protocol used to communicate to this chip. This guy right here, the SI7005, is a Silicon Labs humidity and temperature sensor that we're going to get to in just a second. But as a reference, this chip is only available to communicate over I2C. It's probably one of the simplest communication protocol. It's a 2-wire. You use SCL and SDA clock and data, which has to be pulled up because these pins are configured as open drain, and the only way that you can use these protocol is for both of these lines, clock and data, to be pulled up. For the correct and consistent communication with no hiccups, what you need is you need to make sure that the SCL and SDA are both on the same power rail as the host device, which in this case is this STM32 part. As you can see, STM32 part is powered via a 3.3 rail. So this SCL and SDA, which is powered also from the 3.3 rail, will have an easy time communicating back and forth. That's why it's important to make sure that both chips are on the same rail. And here I have a boot. This boot basically could be used for programming, but it's mainly used to select a flash. Are you using the external flash or are you using the main internal flash memory? Based on the data sheet, it's just recommended to have it pulled low. As you can see on this here, this boot over here is connected directly to ground, but you could basically swap these resistors. You could pull it up to use other memories on the chip. We also have an oscillator. This oscillator is optional because the chip itself has an internal clock that's clocking at 48 megahertz. We don't particularly need an external crystal like in this case, but it's a common package, so I just left it in here in case we wanted to have a more accurate or a very specific frequency to run this chip. But if we're okay with the 48 megahertz main clock that's inside the chip, then this is redundant. We don't really need this. This is just a node reset, so it's basically a toggle. If you press it, it'll be short to ground and basically reset the chip every time you press the button. And I always put this decoupling cap just to make sure that we don't couple noise to these IOs unnecessarily. Here in the bottom, the way that this symbol works is just they have it in two separate blocks. So in this case, we have VDDA, VDDA, and VDDI2. Since this is all on the 3.3 volt rail, I have them all on the same rail, but the datasheet recommends adding different capacitance to each of these rails. For best practice, I made sure that I follow the datasheet and I place the right amount of capacitance at the correct pin.